My authentication system was working perfectly fine in production. We had thousands of users with zero complaints. Then someone sent me a decoded JWT token, and I realized I had been shipping a massive security hole for 8 months. In this video, I'm gonna show you exactly what that hole was and rebuild how you think about JWT from the ground up. We've got 6 sections, and by the end, you'll be able to catch mistakes that most senior engineers miss. Not because they are not smart, but because nobody ever showed them the right mental model. Here is how most JWT implementations are born. You Google JWT Spring Boot tutorial or JWT Node.js tutorial or any other language. You find something with 100,000 views. You copy the code, it works, this is passed, and you ship it to production. And that's the problem. Working in development doesn't mean secure in production. The JWT library handles the mechanics for you. It signs the token, it parses it, but it can't protect you from the architectural decisions you didn't know you're making. It can't protect you from the claims you forgot to validate, or the algorithm you trusted without thinking about it. The worst vulnerabilities in JWT don't throw exceptions. They silently accept bad tokens. Your tests pass, your monitoring shows nothing, and somewhere a token that should have been rejected wasn't. This is what I want to build with you today. Not another tutorial because you've seen a lot. What you need is a layer underneath, the mental model that lets you look at any JWT implementation and immediately know what questions to ask. Above the water, JWT works. That's what everyone sees. And below the water is everything that can silently fail. Algorithm confusion at technique, payloads, no revocation, share secrets across environments. That's why we're going below the water today. Let's start at the beginning, what JWT actually is and why it was built. To understand JWT, you need to understand what came before it and why it wasn't enough at scale. Traditional session authentication works like this. User logs in, server creates a session and stores it in a memory or in a database. The server returns a session ID to the client, usually as a cookie, and on every single request after that, the client sends the cookie and the server has to look it up in the store to figure out who this person is. This works fine with one server, but once you start scaling horizontally, server A, server B, and server C, every one of them needs access to the same session store. That shared store becomes your bottleneck, your single point of failure. Every request has a database round trip packed into it. JWT flips this entirely. Instead of the server remembering who you are, it hands you a self-contained signed token at login. That token carries everything the server needs to verify your identity. And on every request, any server or any instance can verify that token independently without touching a database. No shared session store, no database lookup on every request. Horizontal scaling becomes trivial now. That's the core value proposition of JWT. But this comes with a trade-off that most tutorials don't talk about, and this is important, write it down. JWT is stateless by design, and stateless means you can't invalidate a token after you've issued it. Once you sign a JWT and hand it to a client, that token is valid until it expires. Full stop. You have no server-side record to delete, you have no session to kill. If a user clicks log out and you delete the token from the client, that token is still cryptographically valid. Anyone who has a copy of it can still use it. This isn't a bug. This isn't something you can patch. This is the architecture. JWT is not a session replacement. It's a fundamentally different trust model, and we will talk about how production systems deal with this in the next video. Now let's look at what's actually inside a JWT. A JWT is 3 base64 URL encoded parts separated by dots. Header, dot, payload, dot, signature. The header contains two things: the algorithm used to sign the token and the token type. Simple, but, and I will say this now and come back to it later, this field is more dangerous than it looks. The second part is the payload, which contains claims. These are key value pairs that carry information about the token. The standard registered claims are the subject, who this token is about, issued at, when it was issued, expiration, when it expires, not before time, the token is invalid before this time, JWT ID, a unique ID for this specific token, the issuer, who signed this token, and the audience, who this token is intended for. Look at the if missing or wrong column. Every one of these claims that you don't set or don't validate is an open door. Tokens that never expire. tokens from attacker-controlled issuer, tokens from service A accepted by service B. You have to validate all of them. None of this is optional. And the signature. This is what makes JWT trustworthy. It's a cryptographic proof that the header and payload haven't been tampered with. The signature is computed like this. You take the base64 encoded header, concatenate a dot, and the base64 encoded payload. Run the whole thing through a hashing function with your secret key, and the output is a signature. What this means in practice, if an attacker changes a single character in the header or payload, the signature is completely different. The server recomputes it, compares, and rejects the token. That's the integrity guarantee JWT provides. But notice what it doesn't provide. It doesn't encrypt anything. It doesn't hide anything. It only proves the token wasn't tampered with. And that distinction is exactly what we're talking about next. Actually, everyone told me JWT was secure. Nobody ever told me the payload is completely naked. And you can read it right now, literally. Let me show you something. I'm going to take a JWT, a real one, the kind you would find in any backend systems that uses JWT, and paste it into jwt.io. Look at that. No key, no secret, no password. I just pasted the token into a website and I can read everything in the payload. Username, email, role, anything. Sometimes even there is a database URL here in the payload. This is by design base64 URL encoding. It's not encryption. It's not even close to encryption. Base64 URL encoding does one thing. It transforms binary data into a set of ASCII characters that are safe to put in an HTTP header or a URL. That's it. It's transport encoding. It's not confidentiality. It's not security. Think about it like writing in Big Latin. If you write something in Big Latin, anyone who knows the rules, which is everyone basically, can read it in 2 seconds. The message looks different. It's not protected. Encryption requires a key. Without the key, the data is unreadable. Base64 requires nothing. Any tool, any library, any engineer can decode it in one line. So what does this mean in production? It means the payload is public. Treat it that way. I've seen JWTs in production carrying email addresses, phone numbers, full names, and in one memorable case, an internal database connection string. All of it readable by anyone who intercepts the token. Never do this. The payload should carry the minimum needed for authorization decisions, an opaque user ID, roles, the standard claims we just went through. That's it. If you need the user's email, fetch it from your database using the user ID in the token. Don't put the email in the token. If you genuinely need the payload to be private, if the claims themselves are sensitive, there is a separate spec called JWE, JSON Web Encryption, that actually encrypts the payload. Different tool, different use case, worth knowing it exists. And the worst, attackers can do one-line change in the token header with no password, no brute force, and they gain full admin access. That's no theory. That's a known JWT attack that still ships in production today. And we will talk about that. Let's first talk about signing algorithms. There are 3 you will encounter, and your choice has major security implications depending on your architecture. The first one is HS256, HMAC with SHA-256. This is symmetric. One secret key signs the token, and the same secret key verifies it. Fast, simple, totally fine for a single service with no external verifiers. But here's where it breaks down. In any microservice architecture, any system where more than one service needs to verify the token, every single service that verifies must hold that secret. Service A, Service B, Service C, all holding a copy of the same key. That means your trust boundary is as weak as your weakest service. If one of them gets compromised, the attacker doesn't just have that service's key, they can now forge tokens for your entire system. Every service, every user, he has a full access. RS-256 and ES-256 solve this with asymmetric cryptography. There are 2 keys, a private key and a public key. The private key signs the token. Only your authentication service ever touches it. The public key verifies the token. You can distribute it to every service that needs to verify. You can even post it on the internet. It doesn't matter. A public key cannot forge tokens. Compromise service A, the attacker gets the public key, a key they could have downloaded from your JWKS endpoint anyway. They can't forge a single token. The private key never left your authentication service. RS-256 uses RSA, and ES-256 uses ECDSA. Same asymmetric model, but smaller tokens and faster verification. ES-256 is the modern default. If you're building something new today, use ES-256. And the rule is simple. You should only follow one question. How many services verify the token? If one service is fully internal, then HS-256 is acceptable. The moment you have more than one service verifying, in a microservice architecture, an API gateway, or anything, you need asymmetric RS-256 or ES-256 with no exceptions. Now, those two attacks I teased, and I want you to understand these because both of them exploit the same root mistake, the algorithm none attack. Early versions of several popular JWT libraries, and I mean popular, widely used libraries, had a vulnerability. They read the algorithm from the token header to decide how to verify the signature. So the attacker does this. They take a valid JWT token, they change the algorithm field in the header to none, they modify the payload, set the role to admin, maybe change the subject to someone else, and they strip the signature entirely. The token has no signature. The vulnerable library looks at the header, sees algorithm equals none, thinks okay, unsigned token, nothing to verify, and accepts it. This was a real CVE in multiple libraries and in real production systems. The second attack that shares the same root cause is the algorithm confusion attack, which is more subtle and honestly more elegant in a terrible way. Your authentication service uses RS-256. The public key is by design publicly available. It's on your JWKS endpoint. The attacker downloads it, then they change the algorithm in the token header from RS-256 to HS-256. They modify the payload to give themselves admin access, and then they sign the token using the public key as HMAC secret. The vulnerable server reads HS-256 from the token header, switches to HMAC verification mode, and uses the public key to verify, which is exactly what the attacker used to sign. Signature is valid, token accepted, and access granted. Both attacks, algorithm null and algorithm confusion, have the exact same fix. Your server never reads the algorithm from the token header. Your server has a hard-coded expected algorithm. The token is attacker-controlled input. You don't trust it to tell you how to verify itself. So let's look at what correct verification actually looks like in code. When your backend receives the JWT, here is exactly what needs to happen. 5 steps in this order. Step 1. Split the token into 3 parts on the dot delimiter. Step 2. Decode the header. But your server uses its own hard-coded algorithm. It doesn't read the algorithm from the token. That's the fix for both attacks we just covered. Step 3. Recompute the signature using your key and compare it to the signature in the token. If they don't match, reject. Step 4. If the signatures match, the payload hasn't been tampered with. Integrity is confirmed. Step 5. And this is where most implementations fall short. Validate all the claims. Expiry, not before, issuer, audience, explicitly. Every one of them. Fill any of these steps and you return 401. There is no partial success here. Here is the pattern I see most often, and I want to be clear, this code works. It will parse tokens, it will return claims, your tests will pass. But as you see here, this code reads the algorithm from the token header to decide how to verify. That's the algorithm confusion vulnerability right here in a line that looks completely harmless. No audience validation right here, no issuer validation. This token will be accepted by every service in your system, and it will accept tokens from any issuer in the world. The library checked the signature, but it has no idea if this token was meant for this service or if it came from your own service or someone else's. Here is what it looks like done correctly. Here we are forcing the algorithm and we validate all claims. Unlike the old API, which only validates subject and expiration, we are now validating not before, the issuer, and the audience. You can't call this method and accidentally skip validating a claim. The full production version is in the GitHub repo linked below. The link is in the description below. And I want to make the cost of skipping a claim validation concrete. Look at this table. Missing expiry validation, leak tokens, grant permanent access forever. There is no expiry if you don't check it. Missing issuer validation, an attacker signs up their own authentication server, issues tokens with your user ID, and your service accepts them. Missing audience validation, token issued for your payment service, for example, works on your user service. That's a privilege escalation. Here is the principle. Signature verification proves the token wasn't tampered with. Claim validation proves the token is valid for this service right now. You need both. Signature without claims is a lock with no address on the door. Anyone with any valid token can get in. And this is the mental model I want you to take away from this entire section. The token is attacker-controlled input. Treat it that way. Your server owns the algorithm. Your server owns the validation rules. The token gets to carry data. That's it. It doesn't get to tell you how to process itself. These are 8 of the most mistakes that ship to production every day. Screenshot them. Storing personally identifiable information in the payload. The payload is publicly readable. Using HS256 in a multi-service architecture. One breach, full system compromise. Not validating audience. Tokens work on services they weren't issued for. Missing expiry or not validating it, which makes tokens live forever. Setting expiry to 30 days on an access token. Access tokens should be short-lived. Trusting the algorithm field from the token. Both the attacks we covered exploit this. Using the same secret across development, staging, and production. One environment breach compromises all 3. And accepting tokens without verifying the signature. And yes, this happens in production. And here is what you do instead. Use RS256 or ES256 in production. Asymmetric. Always. Server hard codes the expected algorithm. Never reset from the token. Validate expiry, not before time, issuer, audience explicitly. All of them. Every time. Keep payloads minimal. Only what authorization requires. Use different keys per environment. Development, staging, and production should be fully isolated. Always verify the signature before trusting any claim. And set access token expiry to 15 minutes or less. They are short-lived tokens by design. You now know what most engineers who have shipped JWT in production for years still don't. You know why the payload is public. You know why HS256 breaks in microservices. And you know why the algorithm confusion attack works and exactly how to prevent it. But there is one problem we haven't solved yet, and it's the one that breaks every stateless authentication system. You cannot log a user out. Once the token is issued, it's valid until it expires, period. We talked about logout in section 2, and I told you it was a lie. How do production systems actually solve this? How do you revoke a stateless token? That's video 2, the revocation problem. 4 real strategies with trade-offs and a complete implementation. If you caught a mistake in your own code base watching this, hit like. It helps this get in front of more engineers who need it. Subscribe if you want the rest of this series, revocation, microservices, performance, 1 video a week, all production grade, always real code. And drop a comment, what's the worst JWT mistake you have ever seen in production? I read everyone, and you can find the full production code on GitHub. Link is in the description.